In a remarkable breakthrough that could reshape our understanding of the universe, scientists have unveiled universal laws governing quantum entanglement across various dimensions. This exciting development, which bridges the gap between theoretical physics and quantum information science, was recently highlighted as an editor's suggestion in the prestigious journal Physical Review Letters. The research team utilized a concept known as thermal effective theory, a framework traditionally associated with particle physics, to unravel the complex nature of quantum entanglement in higher dimensional systems. This significant advancement enhances our comprehension of entanglement, moving beyond simplistic one-dimensional models to explore the intricacies of multidimensional realities. At its core, quantum entanglement is a fascinating phenomenon where particles remain interconnected regardless of the distance that separates them. This counterintuitive behavior is fundamental to the development of emerging quantum technologies, including quantum computing and communication. However, the theoretical foundations of entanglement have remained somewhat elusive, particularly when researchers attempt to extend their studies beyond the well-explored 1+1 dimensional systems, which consist of one spatial and one temporal dimension. Historically, scientists have faced considerable mathematical and conceptual hurdles when trying to generalize entanglement to higher dimensions, where the complexity can increase exponentially. A key element in quantifying quantum entanglement is the concept of Rényi entropy, which serves as a measure of the informational complexity and the strength of correlations between quantum states. Rényi entropy is influenced by a variable known as the replica number, which plays a crucial role in determining how the entropy behaves under various conditions. While there is a wealth of knowledge regarding Rényi entropy in lower dimensional theories, its application in higher dimensional contexts has largely been speculative until this recent study. The research team, led by Yuya Kusuki from the Kyushu University Institute for Advanced Study, collaborated with experts from the University of Tokyo's Kavli Institute for the Physics and Mathematics of the Universe and Caltech. They adopted an innovative approach by applying the sophisticated mathematical tools of thermal effective theory, previously used to simplify descriptions of particle interactions and complex quantum fields, to the field of quantum information theory. This interdisciplinary strategy allowed them to extract universal characteristics inherent to the behavior of Rényi entropy in higher dimensional quantum systems. The foundation of thermal effective theory rests on the idea that despite the overwhelming complexity of quantum systems, certain observable properties can be distilled to depend on a limited set of parameters. Among these parameters, the Casimir energy stands out as a crucial quantity that encapsulates vacuum fluctuations and quantum field effects within these systems. The researchers demonstrated that in scenarios characterized by small replica numbers, the intricate dependence of Rényi entropy simplifies significantly, becoming universally governed by just a few physical parameters, including the Casimir energy. This universality extends beyond merely quantifying the value of the entropy. It also sheds light on the structure of the entanglement spectrum, which represents the distribution of eigenvalues that quantify the strength of quantum entanglements within the system. The team specifically examined how the tails of this spectrum, where eigenvalues become large, exhibit consistent patterns dictated by thermal effective theory. Their analysis revealed that these spectral features are not just interesting anomalies, but are fundamentally rooted in the underlying physics across various space-time dimensions. Furthermore, the study explored how different computational methods for evaluating Rényi entropy can influence the observed universal behavior. By analyzing various approaches, the team identified subtle variations in universality that depend on the mathematical frameworks used, contributing to a more nuanced and comprehensive understanding of how to quantify quantum entanglement. The implications of this groundbreaking research are profound, both in theoretical and practical terms. Conceptually, it expands the toolkit available to quantum information scientists by confirming the effectiveness of thermal effective theory in capturing universal features of entanglement. thereby enhancing our understanding of quantum correlations in environments that were previously considered too complex to analyze. Practically, these insights pave the way for improving numerical simulation techniques that model higher-dimensional quantum many-body systems, potentially accelerating progress in quantum computing architectures and error correction protocols. Moreover, the findings resonate with some of the most significant challenges in fundamental physics. Rényi entropy not only quantifies entanglement but also plays a vital role in addressing the black hole information paradox and exploring the delicate interplay between quantum mechanics and gravity. By revealing universal patterns applicable across dimensions, this work brings the physics community closer to reconciling quantum theory with gravitational phenomena from a quantum-information-theoretic perspective. Looking ahead, the researchers are eager to enhance thermal-effective theory with additional layers that cater to the nuances of quantum information. Such refinements hold the potential to uncover even more intricate entanglement structures in complex quantum systems, paving the way for a unified framework that seamlessly integrates quantum theory across various spatial and dimensional scales. The significance of these discoveries goes beyond mere academic interest. A deeper understanding of entanglement structures is poised to have a substantial impact on the development of quantum technologies. By leveraging universal properties of entanglement, future quantum devices could achieve unprecedented levels of stability and efficiency, whether through optimized quantum communication channels or robust quantum simulation platforms that model exotic materials and fundamental particles. In the dynamic landscape of contemporary physics, where the intersections of different fields ignite revolutionary ideas, this achievement exemplifies the power of interdisciplinary collaboration. By merging techniques from particle physics with quantum information theory, the authors have ventured into uncharted territories, providing illuminating insights for the ongoing quest to comprehend the complexities of quantum reality. As the scientific community reflects on these insights, further experimental and computational efforts are anticipated to validate and expand upon these universal principles, potentially uncovering new classes of quantum phases and transitions governed by entanglement. This line of inquiry not only enriches foundational knowledge but also influences the development of future technologies that harness the enigmatic power of entanglement, heralding a new era in quantum science.